Hello guys, and welcome to video number 25 about how to make a chess program in Go. Today we will look into a much better move generator than we had before, where we take use of the transposition table move, the killer moves, and we will also look at the history table that increase the move ordering even better. Let's start with the history table. We have it here. We have a history struct that the first index is 2, is black or white. The second index is 64, it's the from square, and the next 64 is the to square. It's just a counter for every possible move on the board. We don't count every move on the board, but we cover every move on the board. We count only the moves that generates a beta cutoff. And you can see we have an increment that actually doesn't increment with 1, it increments with depth times depth. If we increment only with 1, we will find that down in the tree where the information is less valuable, when it's close to the leaf nodes, we will have the same move many more times. They will get more weight than the moves up close to the root position that are much more accurate. So by doing this, we even out, maybe not 100%, but in some way we even out the difference between the more reliable moves high up in the tree compared to the moves down close to the leaves. There are probably better methods for this increment, but I think this is a good start at least. Okay, we have a clear function to put null in every entry, and also a get to get the actual value depending on from and to square. Let's take a look how it is used. You find it here. It's in the same place as the killer move, where we have a beta cutoff in the search. We add the killer move, but we also increment this history table. When we have a beta cutoff, we run the history inc function. And now the new move generation function. We call it next. And here we can make use of the nice feature in Go that we can handle functions the same as any variable. It's a first-class citizen, as they say in the Go community. So this next function we can fill with any function, because we will use different functions for different purposes. We have a normal move generation, but we also have one for when we are in check. We will not make that today, but we will have, and it's completely different. When we are in check, we need to, most other moves are illegal, so we need to capture the piece or check us or move our king or set something in between, and all other moves are not interesting. And we can have other variations of move generator for other purposes. We go back to the search. Before the move loop, I move this function next normal into next, and after that we can use next as the move generator. And here is the old move generator. It's just a comment now. I have this geninfo struct to keep data between moves and update data between moves. And this SV is a state vector to see where we are in the move generator, because it's made in steps, in phases. And we have the apply, we have the transposition table move. We have one move list with captures, one move list with non-captures, and also the counter move that is not used right now. And here is the next normal function, and as you can see, it's just a big switch on the state vector with its different values in it, next, and so on. And all the different states or steps in this move generator, they are here. We have an init, but after that we have the transposition table move, and then we have the first good capture and the rest of the good captures. These are together, but I will show that why I do like this. Everything starts with next. That might be confusing, but that's just why the function is next. We have the killer 1 and killer 2 and the counter move, and then we have the first non-capture move and all the rest of the non-capture moves, and finally all the bad captures that we think are the bad captures. Here is the function, and first we go to the init next. It doesn't do anything, it just goes through the fall through and goes on to the next. I set the state vector to next TR, transposition table move. And there I set the next step, next state variable to first good capture. But first the transposition move, if it's a move, we check that it is legal, and then we return that move. So that move will be searched. And when we come back, the state vector is next first good capture. If we didn't do the return, either it was a no move or it was not a legal move, we come down to this fall through and continue with the next first good capture. And here you can see why we have these two functions. One is first good capture and the rest of the good captures, because here we generate all the captures, and with use of the C function we try to find out which capture is good or not. If we find a good capture, we will set the state vector to next good capture and return this first move that we found. If we didn't find any good capture, well, then we set the state vector to the first killer move, because no need to continue with good captures. And when we come back, we continue with good captures, but this time we don't need to generate any captures. That is already done in the first good captures. And we continue with good captures. We return good captures until we don't find anything more. We come down to this state vector killer 1 and fall through to that step. And then we continue with the first killer move and return that. It must be legal, of course, and we continue with killer 2 move, the second killer move, and return that, and it must be legal. And of course they cannot be the same as the transposition move, so we don't want to generate the same move several times. And then we go to counter moves that we don't have right now. And after that we have these two non-capture steps. The first non-capture, that is generating all non-capture moves, and pick up the best of all the non-capture moves. And to do that we use the history table. We pick from the history table. And when we find one move, before we return it, we do this little trick by replacing that move, the best move, with the bottom move in the table, and we remove this move from the table. And then we continue with the next non-capture move, and now we don't need to generate all the moves, we have them. And we do the same thing here. We return one move at a step and use the history table. And finally we have this next bad capture, all the bad captures. These are the remaining moves in the capture move list. And as we can see from the tests I did, I think we increased our efficiency with 10% or something like that for the start position, and maybe 20% for the Philidor, and even more for the English and the London position. The London position was even 30%, I think. Even the nodes per second increased, just because a better move generation function. That's all for today, and until next time, have a good time unit.